What if the expansion of the universe ends? It's challenging to make end-of-the-world predictions. Even more difficult to anticipate is the end of the cosmos. Scientists have predicted how our planet would end naturally. The sun will eventually exhaust its fuel, turn into a red giant, and then eat our planet Earth. Our beloved sun will grow in size and swallow the nearest planets before exploding into a planetary nebula and leaving behind a dense white core known as a white dwarf. We are aware that our galaxy and our neighbor, the Andromeda Galaxy, will collide in 4.5 billion years. But because we still don't fully understand how our universe began and the physics that underlie that, the end of our universe is something that is very difficult to forecast. We can attempt to forecast some potential outcomes for our universe by considering the cosmos's ongoing expansion and the unidentified factors that are driving it. And what will happen after this expansion stops? What would happen if every galaxy, star, planet, and object in the universe suddenly ceased drifting apart from one another? Would the universe simply freeze in place as it is? Or would it disintegrate into a single point, as it did before to the Big Bang? What if the universe stops expanding is the topic of this video. Astronomers need to understand the past of the cosmos in order to forecast its future. Cosmologists tend to look backwards since the only evidence they can look at with telescopes is far away and relates to events that happened in the distant past. Through a combination of physics and conjecture, they use the velocity of far-off stars and galaxies to forecast potential future events. However, how did it all start? The Big Bang Theory serves as the foundation for this idea. It is the dominant cosmological theory that explains how the universe has existed from the earliest known times to its subsequent large-scale evolution. Early in the 20th century, scientists hypothesized that the universe's expansion may slow. The gravitational field of the Earth causes a ball you throw into the air to eventually fall to the ground. They believed that the universe we live in should experience the same thing. That the universe's gravitational force will eventually lead the expansion to slow down. However, Hubble discovered that the universe was still expanding when he pointed his telescope upward in 1920. Vesto Slipher made the first observation of the universe's expansion in the early 1920s, while Edwin Hubble, who had access to some of the biggest telescopes in the world, provided the Hubble law in 1929. It states that every far-off galaxy is separating from the others at a velocity proportional to its distance. The velocity at which a galaxy is moving away increases with distance. Then, Arno Penzias and Robert Wilson discovered an omnipresent backdrop of microwave radiation that is now known as the cosmic microwave backdrop, CMB, radiation. It was the scorching, dense afterglow of the primeval fireball. Since the Big Bang accounted for the light nuclear isotopes like deuterium, hydrogen, helium-3, and others, today's data from the Cosmic Background Explorer, COBE, satellite completely matches with this theory. The idea of a catastrophic explosion followed by inflation is supported and proved by scientific facts available today. They were once again taken aback by this. They proposed the concept of dark energy, an imperceptible dark energy that is accelerating the growth, to explain this. Because this force doesn't interact with ordinary matter or any other electromagnetic forces, they refer to it as dark. It should be mentioned that the term universal inflation is somewhat misleading. Our cosmos is expanding even if nothing in it is moving. According to theories, the reason why it looks to be increasing is because the space is actually expanding while it fills. So what if this energy's intensity gradually diminishes over time? According to our understanding, the cosmos might have one of three outcomes. Whether this expansion will continue, pick up speed, or slow down will determine the future of the cosmos. The universe may someday be torn apart by this expansion's rate, causing it to end in a big rip. As an alternative, the universe might shrink, decline, or shrink, reversing the Big Bang and annihilating everything in a big crunch. The Big Freeze is the name given to a third hypothesis. However, we won't go into much detail about the other fates in this video since we are talking about what will happen if the growth stops. Every galaxy outside of our local cosmic neighborhood is rapidly elongating away from us. It is possible that the cosmos will experience a fate known as Big Crunch if this expansion ceases. Things will temporarily come to a standstill when the universe's expansion ends and everything in the cosmos stops moving apart from one another. But soon, the gravitational force of all the other matter and dark matter will rule our universe. The expansion of our universe would be reversed since gravity would be the dominant force and act in the opposite direction. This would ultimately lead the universe to contract, resulting in the collision of stars, planets, and entire galaxies, effectively causing the universe to collapse in on itself. Over time, galaxies and ultimately individual stars will collide more often, eradicating any life that may have existed on surrounding planets. In the closing seconds, everything will burn out in a single point as temperatures and densities climb in a contracting inferno. Simply said, as the universe continues to expand slowly, the Big Bang occurs in reverse, collapsing everything into a singularity. Right, this looks like an interesting potential. The singularity of the universe returning, the beginning of a different universe, could occur as a result of this singularity exploding into another Big Bang. Many scientists nowadays still adhere to the cyclic theory of the universe. What about the physics laws, though? Would the universe's entropy lessen? Would the passage of time reverse? We aim to address these and other intriguing questions in this video. One of the most significant symmetries in all of physics is the time reversal symmetry. Simply put, it asserts that whether the clock is running forward or backward, the principles of physics apply. Here are a few instances of this phenomenon. A collision that is entirely elastic, such as the impact of two pool balls, would react precisely the same whether time is moved forward or backward. The way electromagnetic and gravitational interactions operate is constant. The weak nuclear interactions are the only ones that deviate from this symmetry, and if your system is complex enough, you'd need to know its exact locations and momenta with more precision than is quantum mechanically achievable. If we ignore it, all other physical rules are actually the same regardless of how time is measured. Simply put, it means that, excluding weak interactions of course, there is always a method to return to your original state if you apply the right sequence of interactions in the proper order after arriving at any final state instant in time. But it doesn't seem like this holds true for all of the things we encounter on a regular basis. There are some phenomena that are obviously one way. For instance, if you break an egg, you can never undo the damage. The second exception we noted before, these are undoubtedly complex systems with incredibly sophisticated sets of interactions. Now, if you apply time reversal symmetry to an expanding universe, you'll get a contracting universe. Since contraction is the opposite of expansion, a universe that is contracting would result from turning the hands of time backwards. However, there will still be certain events. Let's look at them. Particles that fall into or form a bound structure nevertheless exchange energy and momentum through elastic and inelastic collisions, proving that gravity is still an attractive force. The particles of ordinary matter will still lose angular momentum and collide. They will continue to go through atomic and molecular changes, emit light, and produce other types of energy. Simply put, in a contracting universe, everything that increases entropy today will continue to do so. Entropy will therefore increase even if the cosmos shrinks. The creation and presence of supermassive black holes is the primary source of entropy in our universe. The entropy of the universe has increased by around 30 orders of magnitude during the last billions of years. 1 second after the explosive Big Bang, the entire universe had more entropy than the supermassive black hole at the center of our galaxy, the Milky Way. Time will therefore continue to advance, and the Big Crunch would have occurred at a much higher level of entropy than the universe had at the beginning of the hot Big Bang. When all supermassive black holes' event horizons start to overlap, all of the energy and matter will start to combine under the most extreme circumstances. This would be the most likely scenario in which gravitational waves and quantum gravitational effects will manifest on macroscopic scales. Our universe would create a gigantic black hole with an event horizon billions of light years wide if all the matter and energy were condensed into such a small space. The intriguing aspect of this situation is that when you are close enough to a large enough mass and are subject to a strong gravitational field, clocks behave differently. We would unavoidably find ourselves near the edge of a black hole's event horizon if the universe were to collapse once more and approach a big crunch, at which point time would begin to swell for us, stretching our final instant into infinity. As our universe was ultimately destroyed in a big crunch by the merger of all singularities, a sort of race would be taking place as we descended into the center singularity of a black hole. What will occur next, then? Will our universe still exist, or how will it look? Would the universe simply disappear in a wink? Would it result in the creation of a brand new universe, as the cyclic model predicts? Would there be some type of cutoff where we could only enter the crunch scenario up to a certain point before the universe recovered, causing some kind of rebirth but avoiding a singularity? These are some of the fascinating theoretical physics topics that researchers are working to resolve. One thing, however, seems to hold true regardless of the situation: time always moves forward and the entropy of our cosmos continues to increase. In the unlikely event that this is incorrect, there is still something basic about the nature of reality and physics that we have yet to fully understand. What are your thoughts on these inquiries then? Please share your comments and suggestions below, and don't forget to like, share, and subscribe to our channel.